So these are notes for Unit 5, Day 16. And they kind of start on page 41. 41 was a data collection, and we got through that first example, and we're going to continue with the examples. So we're still working with the essential question: how can derivatives be used to maximize and minimize values? And this example that we're going to look at here is a no calculator example. So we're doing this analysis by hand. And so the question is: a rectangle with sides parallel to the coordinate axes is inscribed in the region enclosed by the graph of y equals minus 4x squared plus 3. So it's a parabola. Inscribed means inside. And so we see a graphic of that scenario right there. So this rectangle is enclosed by the graph of the parabola and the x-axis. So considering that's the inside of the inscribed rectangle. This is find the dimensions of the rectangle having maximum area. So we're trying to maximize area. So that being the case, we know that the area of this rectangle is base times height. Well, the base is 2x, because since this is the coordinate axis, it's over from the y-axis. So we're over x in each direction, which means we have a length of 2x. We have a height of y, which is the value of the function. So there is the model or the formula I need to maximize. I got to write that in terms of one variable. So we know that y is dependent upon the location on the parabola. So that's the constraint, is that this point right here has to be on the parabola. So that gives me a equals 2x times the quantity minus 4x squared plus 3. I'm going to go ahead and distribute that. And then now I can, if I want to maximize this area, I want to know where the derivative of this is equal to 0. That's finding the horizontal tangent lines. So I'm differentiating this function for the area, getting a prime, and I'm setting it equal to 0. And then I'm going to go ahead and solve that. So bringing 24x squared to the right side, dividing by 24, gets us 1/4. So we have x squared equals 1/4, which means when I square root it, x is equal to 1/2. We really could say plus or minus 1/2. And you know, relative to this picture, that makes sense. We could either be over here at plus 1/2 or over here at minus 1/2. And now we have to answer the question. It says find the dimensions of the rectangle having maximum area. So we know maximum area occurs when x is equal to 1/2, but x is only this distance here from the y-axis to the edge of the rectangle. So the dimensions of the rectangle then, in order to answer the question, the direct dimensions of the rectangle are this across the bottom x-axis, and this parallel to the y-axis. So that means if we calculate the area, we have an area of 2, and the dimensions then are 1 by 2. So you can see here's the width of 1 and the height of 2. And so confirming that it is a maximum value, we look at the candidates test here. So the candidates test is saying we got an answer of 1/2. And we know that if our x value were 0, we had 0 width here, we'd have 0 area. And we know our maximum width would be, or not a maximum width, but our other extreme area value is going to come from having the entire width of the rectangle be from left to side to right side of the parabola. But to be inscribed then we have a height of 0. So also an area of 0. So we can see by the candidates test using these constraints as the endpoints that at 1/2 we're reaching the maximum. So we know that that's the value of the maximum area. So to answer the question, we have a 1 by 2 rectangle having a maximum area of 2 square inches. Okay, so looking at example 3. Says for the function y equals 2 times the square root of 4 minus x, what is the coordinate of the point on the function's graph that is closest to the origin? So we know the origin is 0, 0. So when x is equal to 0, y is equal to 4. So I'm setting up to kind of a general sketch. This is a no calculator. So I know this is a sideways parabola. So let's just start graphing a few points that are convenient. So when x is equal to 0, 0 in here, square root of 4 is 2, 2 times 2 is 4. So I know I have that point. When y is equal to 0, that means 0 out here. That means we have 4 minus the square root of x equals 0. And so we have x equals 4. And we, like I said, we know it's a sideways parabola. So we've got, I just grabbed another point here. -5 is convenient because it makes us 9. 2 times the square root of 9 is 2 times 3, and that's 6. So here's a basic sketch of the sideways parabola. And we want to pick the point along this red parabola here that's closest to the origin. Now, just common sense, we can see that we're a distance of 4 away if we're right here. We're a distance of 4 away if we're up here. Obviously, if we're out here, we're farther. So our answers, our solution is not going to be in that location. Our solution is going to have to be somewhere between an x value of 0 and an x value of 4. So that's going to, well, this is the sideways parabola is our constraint. These are going to be our endpoints in our candidates table. Okay, so we know that we want this distance here from the origin to some random point on this parabola. And we know the distance is basically the hypotenuse of the Pythagorean theorem. So if you notice, if I start putting in dashed lines here, drop a vertical down, we can see a right triangle there. So our distance is x squared plus y squared, and then take the square root of that. So that's basically the hypotenuse. So that's what we're trying to minimize. So we need to get this mathematical relationship in terms of one variable. We'll stick with x, and for y, we're going to put in this value right here. And we're going to substitute that in here, and that's going to make it look really confusing. But here's the cool thing. If we want to minimize distance, all we really have to do is minimize the square of the distance, which means all we really have to do is minimize this, which is a lot easier to differentiate than this. So I'm going to go ahead and substitute in the value of the function, and I'm going to simplify this. This squared is just 4 times 4 minus x. So 4 times 4 minus x, there we go, that's squared. I'm going to distribute this. And I'm going to rewrite this so that, oops, I guess I don't rewrite it. So we're looking at the distance squared. I can just differentiate this because the derivative of this is going to be like, it's going to be, as long as I'm just setting it equal to 0, it's going to be finding the same value as when the square root is on top of it. So when I take the derivative, this is kind of a weird notation, but I have the distance squared and this little hash mark is the derivative of that. It's 2x minus 4. I'm going to set that equal to 0. And when I solve for x, I get an x value of 2. So when x is equal to 2, we are the closest, so that's right, this is x is equal to 2, so it must be this location here. That puts us at the closest point to the origin. So checking, going back to the comment about needing to be in this part of the parabola, setting up our candidates table, if x is equal to 0, then it shouldn't be area, it should say distance. Then if x is equal to 0, we know we're a distance of 4 away. We can actually just count the boxes. We can also put in, this is really the distance along the y-axis, so we could calculate that there too. When x is equal to 4, then we also know we're a distance of 4 away. And so at x equals 2, we're a distance of square root of 2 away, or square root of 12 away, excuse me. And so we get that by substituting 2 back into this expression and square root. And so that is definitely a minimum value. 4 is representing that. So when x is equal to 2, the distance is a minimum. Oops. And let's see if we answered the question right. For the function was the x coordinate. That's what we were defining as when x is equal to 2. And then this candidates table helps us verify that this is in fact the minimum value. Minimum distance. Okay, so just looking for keywords here and identify, so it's easier to identify optimization problems. Maximum obviously would be something to maximize. The word maximize, or the word most, or greatest, or fastest, or furthest. Those are all indications that you have an optimization problem and you're looking to maximize something. Similarly, if you see the words minimum or minimize, least, smallest, cheapest, closest, those are all indications that you have an optimizing question. It's asking you to find a minimum. So some common question stems are things like this. Find the dimensions of the field with the largest area, or the greatest area. Find the ordered pair that is closest to a given pair. Find the time when the particle is furthest from the origin. Find the height of the box requiring the least amount of material. So those are all using those synonyms for maximizing without blatantly saying, I want you to optimize this and maximize that area. So those are kind of the ways we can reword something and an optimizing question. Okay, so when we get into the classroom, we'll go over these comments as our takeaways from the notes, and then we'll work on some topic questions.